It's gonna be a really easy lecture. We won't be proving much. So the lecture is called Hardness of Problems on Lattices, and here's the outline for this lecture. We'll first define this, the main problem on lattices. Then we'll see some of its applications. We'll see motivation of studying this problem. We'll talk a little bit about hardness of this problem, and then we'll try to prove that it's somewhat hard under the SETH assumption, strong exponential time hypothesis. Okay, so in order to define the closest vector problem, CVP, I will first introduce lattices. So by lattices, we will mean the following structure. Say you give me n vectors in some Euclidean space, and then lattice is just a set of points, infinite set of points, which are integer combinations of these vectors. That is, I'll show you an example in a second. You can take the first vector plus 3 times the second vector and so forth. It's a set of all integer combinations of those vectors. Here, by n is called the rank of the lattice, and d is the ambient dimension, but we won't care much about d in this talk. We'll always be talking about n, the rank of the lattice. How many, in general case, linearly independent vectors you have? What's the dimension of the lattice? And here's an example. I give you 2 linearly independent vectors, b1 and b2. Then this point, which is b1 plus b2, is a point in my lattice, because b1 plus b2 is an integer combination of 2 basis vectors. This point, which is 2b1 plus b2, is also an integer combination, so it's also in my lattice. In general, all these points belong to my lattice. And here, this lattice is super simple. You can easily understand what points belong to this lattice, what points don't belong. You just have a bunch of these parallel lines, right? If you want to go from one line to another, you take vector b1. If you want to walk through one of these lines, you take vector b2, positively or negatively. It's very, very simple lattice. You understand basically everything about it. In particular, if I ask you what's the closest point to this point T, what's the closest lattice point to this problem T, you just tell me this is this one, right? Because you understand that T lies on this line. I can just be walking through this line by taking positively and negatively the vector b2, and I find the closest one. That's easy. And this is exactly the closest vector problem. I'm giving you a lattice as just a bunch of linearly, n linearly independent vectors, give you a point, and I'm asking you to find the closest point of this lattice to my T, which is target point. But what about this lattice? I give you this basis, b1 and b2, and give you this point. Which point of the lattice is the closest one to T? What do you think? So one might think that this is b1, but actually this is the basis for very same lattice, just a weird basis, but it gives me the same lattice. And then the closest point to T is actually this one. It's not what you might have originally thought. And this is exactly where the hardness of lattice problems comes from. If I give you a very nice basis under some definition of niceness, all the problems are easy. If I give you a bad basis, then problems become hard, actually NP hard. And this is the definition of the closest vector problem. I give you a basis n linearly independent vectors, and I give you a target point. And I ask you to find the closest vector, or maybe just distance to this closest vector of the lattice. Does the problem make sense? Again, feel free to ask questions. It's a good point to ask a couple. Yeah.
I don't understand. Is it true that there is no limit points?
That there is no what?
Points. So, I mean, infinitely many points that go closer is closer to something.
No. This is this is a lattice, right? This is a discrete set of points. That's what you mean?
Yeah.
I mean, if we take an line to
Right.
And the lattice will have...
They're linearly independent. No, it always has the structure in the sense that this is like basic parallelepiped, and you just copy it million of times. Does this answer your question? Or you can just take any parallelepiped generated by your basis vectors and just replicate it million of times in all directions, infinitely many. Does it address the question? Yeah. Great. Okay. And for any p from 1 to infinity, we can define LP norm of a vector like a normal Euclidean norm. L2 is just square root of sum of squares. But for other p, we just define it as 1 over p's power of the sum of p's powers of the absolute values. And when p is in infinity, we take this like limit of this and have the maximal absolute value. This is how LP norm is defined. And we can define this closest vector problem, or CVP, in terms of LP norm as well. For every p from 1 to infinity, we can define CVP as like I give you a basis, I give you a target point, find me the closest point with respect to this distance, LP. When we're talking about Euclidean distance, we're talking about CVP2. Okay. So this is exactly what our problem looks like. I give you basis target point, and you return me this point. And let's see why this problem is interesting. So algorithms for this problem give us many other important algorithms. For example, the first algorithm for this problem gave us polynomial time algorithm for factoring polynomials over the integers. We also, like, from algorithms for CVP, we get algorithms for integer programming. For example, that's like how we for the first time solved integer programming with a constant number of variables in like polytime. And still, like, the best algorithms for integer programming use algorithms for CVP. And also, it's widely used. It used to be widely used in cryptanalysis for crypto systems, which were popular in like 80s and 90s, like based on knapsack problem and similar problems. But one of probably the main applications is lattice-based crypto. Let me, on problems similar to CVP, on their like gap versions, you can actually build crypto systems. And these crypto systems are cool. Let me try to convince you that they are cool. We know that there is like RSA crypto system, which is widely used now in real life. One problem with it is that if we ever build quantum computers, we'll break RSA, we'll break almost like all encryption we currently have in real life. For lattice-based cryptography, we conjecture that quantum computers cannot break it. We can't prove it yet, of course, but it's conjectured quantum security at least.
It is conjectured just because we don't know?
Just because we've studied it for decades and couldn't find it, yeah. Also, it is super efficient in practice. It's both like efficient in terms of running time, it's easy to parallelize, and it's not hard to implement. Also, what we really want for cryptography, when we're talking about cryptography, we say there is a difference between like P versus NP questions and questions we need in cryptography. And the following terms, like in P versus NP, we say there is a problem which you cannot solve in the worst case. Maybe you can solve it in 99% of the cases, but like sometimes you cannot solve it. When we're talking about cryptography, we usually use assumptions like on average this problem is hard. That is, like, for most of the inputs you cannot solve it. And this is much stronger assumption than just NP hardness. What is great about lattice-based cryptography is that it's actually based on worst-case hardness. In lattice world, you have worst-case to average-case reduction, and if you prove that a lattice problem is hard in the worst case, you automatically get average-case hardness, and you get cryptography. This is something what we really want in cryptography. To prove that this system is secure, you just need to prove NP hardness kind of result. You just need to prove that in the worst case, you cannot solve this problem. Also, from lattice primitives, you can construct crypto primitives which we don't know how to construct from normal crypto assumptions, like existence of one-way permutation or even public key crypto. There's fully homomorphic encryption or attribute-based encryption. There's incredibly powerful and practical primitives which we don't quite know how to construct from normal problems, non-lattice problems. And the nice thing about lattice-based crypto is that it's about to be deployed. Here is a good implementation of a crypto system based on lattice problems. It's already available on GitHub, and the American National Institute of Standards, which basically standardizes their default crypto primitives, has just recently had a call for like post-quantum or lattice-based cryptography. So they're currently considering different lattice-based encryption protocols. It might become standard soon. Google starts seems to start using this, and in a couple of months, the Gödel Prize for this year will be awarded to Adet Regev for basically developing this crypto-based, lattice-based cryptography. Okay. What do we know about the hardness of this problem? First of all, we know that this problem is NP hard for any value of p. The closest vector problem is NP hard, and we'll see that p is that norm, CVP problem in the LP norm. It is NP hard for any p, and we'll sketch this argument in one of our reductions soon. But again, NP hardness doesn't tell us anything about quantitative hardness of the problem, right? Maybe this problem is solvable in like quasi-polynomial time. We don't know. We just know that it's unlikely that we will find a polynomial time algorithm for it soon. We know how to solve this problem, say in the Euclidean distance, in time roughly 2 to the n. And we know actually 2 algorithms for it. And both of them stuck at the bound 2 to the n. Like, we just don't know how to improve them. It's not like we don't have enough technical tools. We have no idea how to improve on the running time 2 to the n. We're really stuck there, so it would be nice to prove a lower bound of 2 to the n. That's more or less what we're going to be doing today. And the third kind of motivation for this question is that, again, there are crypto primitives based on similar problems. And if you manage to solve the CVP problem in time like 2 to the n over 20, you actually break these primitives for real-life implementations, for real-life values of n. So we actually want to conjecture 2 to the n hardness or something close to it of these problems.
Do you mean this complexity for every p?
Here it's we're talking about p equals 2. Yeah. The most important case is a Euclidean norm, p equals 2. But we'll see that we fail to prove good lower bounds in this case, but we'll prove lower bounds for every other case. So, yeah, the important one is p equals 2, Euclidean distance. Yeah?
What is the exact inputs of the problem? I mean, you said that all vectors are from R to E, from real numbers.
Yeah.
How do we inputs?
Like normally you can say they're like say rationals, or maybe you can normalize them and make integers. Yeah.
And the output is a point.
Either a point or the closest distance, or if you want a decision version of the problem, then I give you lattice, point, distance, and you tell me is there a point in the lattice and at most this distance or not. But yeah, usually you return either the closest point or the distance to a closest point.
Also rational, yes.
Sorry?
Also rational.
Yeah, say like a reasonable approximation of it. Yeah.
There is some figures parameters.
Say reasonable approximation. Yeah, you can define it. Say for every epsilon, you can return it with. Yeah. or just or say lattice all vectors are integer vectors, and you just return integer closest vector, yeah, which is, then you don't have to talk about non-rational numbers. Other questions? Okay, so just to recap, we've considered this k-sat problem. By n we denote the number of variables in it, by m we denote the number of clauses, and each clause is of length at most k. And we said that, roughly speaking, SETH, strong exponential time hypothesis, says that k-sat cannot be solved in time 1.99 to the n. Yeah, and now we want to prove hardness of the CVP problem. How do we do this? We reduce sat, like k-sat to CVP. Just if we want to prove a lower bound of 2 to the n, which we do, then we want to make sure that we reduce a sat on n variables to a lattice with n vectors, possibly in higher dimension. We don't care about dimension, but the number of vectors should be n. Questions? Okay, don't be scared. I'll explain every single character on the slide. I have to have one technical slide here, but it's like super easy idea. We want to reduce k-sat to CVP. Let's start with 2-sat. It's not quite useful because 2-sat is not even NP-hard. It's just like a toy example. We'll start with 2-sat. And here is my lattice. What I mean by this, that this is the first vector in my basis. This is the second one, the third one, the nth one. And this is my target point. This is just name of the column, names of the rows. Again, this is the first vector, coordinates of the first vector in my basis, second, and the nth one. And alpha is some like huge parameter. So this is my lattice. I want to say this is a good reduction from 2-sat to CVP. What I mean by a good reduction, there exists some, just if you return me a point which is really close to the lattice, then I'll say that 2-sat is satisfiable. If it's far away, then it's unsat. This is the target point. We're going to be computing the distance from this lattice to this target point. And why does such a reduction?
Could you tell a little bit more? So for each, so what if we close?
Oh yeah, right. Here I have. So each column is numbered by a variable from the sat formula, and I have 2 sets of rows. The first one contains n rows and is just 2 alpha for a huge alpha multiplied by the identity matrix. And second one is for every clause, like I'll now be considering only clauses with like positive literals for simplicity. But say I have x1 or x2, then I just write 2 here and 2 here, and 3 in the corresponding coordinate of the target vector. If I have x1 or xn, I write 2 here, and 3 in the target vector. Yeah? Yeah, I just said for simplicity I'm considering only positive ones, but if you have negative ones, you do the same thing, just here instead of 3, you'll have 3 minus 2 times number of negative literals. It doesn't matter. Let's for simplicity focus on the positive ones.
Yeah, just to clarify, so you are now reducing the 2-sat
Right.
belongs to P.
Right.
And not only this, but also a special case where there are no negations.
Exactly. Yeah. Yeah. Okay, so let me show you what this reduction does. Assume alpha is very huge. Then what's the solution to the CVP problem? You tell me that you take the first vector, like some integer number of times, then you add second vector times some integer and so on. So assume you give me a solution to the CVP problem. If it happened to be so that each vector is taken either 0 or 1 times, which is actually my goal, because I want to map sat assignments to however many times you've taken each vector. So if it happened to be 0, 1, which is good for me, then here you have coordinate either 0 or 2 alpha. Here you have either 0 or 2 alpha. Here you have either 0 or 2 alpha. And in the target point, you always have alpha. So your distance will always be alpha, like to the power of p or whatever. Make sense? If you take it either 0 or 1 times, the distance is always alpha. But if you take at least one vector like twice or -1 or any like non-zero 1 times, then the distance will be much larger. For a huge alpha, this I'll just in the end I will see that your point is really far away from the lattice, so you didn't find a good assignment. This simple gadget to alpha times the identity matrix just lets me distinguish the cases where x is 0, 1 or not 0, 1. That's what I want, and then I want to make sure that this 0, 1 assignment also satisfies all clauses.
So this is not exactly the distance, but the piece power of distance.
This is, yeah, piece power of the distance, yeah. So a non-zero 1 assignment contributes too much to the distance, and using this I can distinguish them. Now let's look at the second part. Assume x satisfies some clause, say this one. Then this means that I've taken this guy or maybe both of them. So sum of coordinates in this row will be either 2 or 4. And again, distance from both of them to 3 is exactly 1. But if you don't satisfy this clause, then your distance is like distance from 0 to 3, which is 3 to the p, which is again larger than the good distance. So this gadget lets me distinguish between SAT and unsat assignments. So this means that if there is a close point to this lattice, then the original formula was satisfiable. If there is no such point, then it wasn't satisfiable. Is this clear? Yeah. The only problem with this reduction is that it reduces to SAT, which is like way too simple problem. What is nice about it is that, okay, how does it work? Given an instance, I reduce it. If all clauses are satisfiable, distance is small. If not clauses are satisfiable, distance is large. But I can actually look at this threshold. If you satisfy, say, m over 2 out of m clauses, I can understand this by distance as well. Once I see the distance to the lattice, I can actually understand what the maximal number of clauses you can satisfy. If you satisfy all of them, you're very close to my lattice. If you satisfy many of them, you're still somewhat close. So just looking at the distance, I can understand how many clauses you satisfy. So this reduction actually gives me the maximum number of satisfiable clauses, which is actually already at least NP-hard problem. This problem is called max to SAT. So let me explain what this is. Given a 2-SAT formula, just understand whether it is in SAT or not is a simple problem. We saw in the problem solving session that you can solve it in linear time. But the following question, what the max number of SAT assignment, max number of SAT clauses, that is, go through all assignments to the Boolean variables and check how many clauses each of them satisfies. Choose the maximum. So this problem is NP-hard. So we just reduced an NP-hard problem to CVP. In particular, we proved that it's NP-hard. Questions? And this works for every P. Like I wrote those distances in terms of P, it works for every P. So the question is it actually to find the maximum number, or is it check whether you can satisfy at least k of them? Both problems are NP-hard, just like one of them is search version, one of them is decision version. If you want to be talking about like NP-complete problems, then yeah, you probably want to have this parameter k and check whether you can satisfy at least k. But they are more or less equivalent problems. Other questions?
More precisely, to NP complete.
Which one? If you want to check whether you can satisfy at least k clauses, yeah, it is NP complete.
It is NP hard, but actually it's
Yeah, yeah.
in NP.
Okay. What is also nice about this reduction is that max to sat is a somewhat hard problem. Until 2005, we hadn't known any algorithm which solves this problem in fewer than 2 to the n steps. Now we have algorithm 0 to Ryan Williams, which runs in time 1.74 to the n and uses exponential space. For example, we still don't know how to solve this problem in time less than 2 to the n with only polynomial space. So this problem is somewhat hard. You can, for example, conjecture that this problem is 1.74 to the n hard. And from such a conjecture, you immediately get such a hardness of CVP for every p. Just because we didn't blow up the parameter n. From n variables, we get a lattice on n linearly independent vectors. So this is some conditional hardness of CVP. Under some assumption, you can say it's like that hard. Our goal is to prove 2 to the n hardness. And soon we will see how badly we fail. Yeah?
So I guess there is a reduction from first sat to max 2 sat.
Sure.
Is at least the linear.
Right, yeah. Yeah, you can say that max to sat is exponentially hard under ETH. That's what it is, yeah. All right. Other questions? Okay, so we've just reduced 2 sat. To get hardness from SETH, we want to reduce every k sat. I want to say that for every k, we can reduce k sat to our problem, and then we get SETH hardness. So how do we generalize this reduction to k sat? Once we have this, yeah, under SETH, we say it's like 2 to the n hard. So we just said in that reduction that 2 CNF clause is satisfiable if and only if you have either 1 or 2 literals satisfied in this clause. And we said that between 1 and 2 we can pick this point like 1.5. It's on equal distances from 1 and 2. That's why our reduction worked. We said that you satisfy either 1 clause or 2 clauses. You have some in this row, either 2 or 4. And point 3 is exactly in between. So the reason why we could get this reduction was because there is a number between 2 and 4, and this is 3. For k sat, we would like to say that there are k numbers which are on the same distance from 1 of them. And this is impossible. Online, you cannot pick. What we did for 2 sat, it was 3 equal distance to 2 and 4. It's hard to find other points like with this property. What we can do instead is that, what if instead of k numbers, we'll find k vectors? This might be easier. And this is exactly the point. Instead of looking at one line, we'll be looking at like k-dimensional space. And we'll say there is a point such that all these guys are on the same distance. Okay. So our goal from now is to find, for every k, we want to find k vectors such that if you don't satisfy the clause, which was you don't take any of these vectors, you just multiply it by 0, then your distance to some target vector is large. Since you don't take any of those vectors, this is just the length of the target vector. If you take at least one of these vectors, maybe all of them, maybe some subset of them, then we want to say the distance is exactly 1. We want to find k vectors such that each of them corresponds to a literal in a k clause. If you take at least one of them, the distance to some target point is exactly 1 because you satisfied this clause. You want a distance to be small. If you don't satisfy this clause, which is equivalent to saying you don't take any of your vectors, so you multiply your vectors by 0, you just take the target point basically. The distance is larger than 1. So for to reduce every k sat, you want to for every k find a set of k vectors and the target point with this property. Is this clear? then the absolutely same reduction would work. Just instead of this simple gadget with 2, you will be taking vectors in some larger dimensions. But as I said in the beginning, we don't care much about the dimension of the space, ambient space.
So does it imply immediately, does it give a reduction immediately, or do you still need to deal with negations in the closed?
No. Negations are, seriously, they're just for free. Just say you have a negation here, you know that if you satisfy it, like your sum will be like either 2 or 0. So your target point should be 1. I just like, okay, I want to say that x's are actually not 0, 1s, but plus minus 1s. But this is just a fine transformation of the lattice. It's like you get it for free.
So only target function changes.
Sorry?
If you add negations, then only target point.
Only target point changes, yeah. But like for this, you better apply this affine transformation, which says that x is actually minus 1, 1, not 0, 1. And then here, just if you satisfy this clause, then say x2 is negated. Then how can you satisfy it? Either like by 2 or by 0 or something like this. And your target value should be like 1. Then. Yeah. No, negations are free. And the main point here is that instead of just the simple numbers, you should be considering vectors. And then instead of just writing 2, you'll write some m-dimensional vectors there. You'll blow up the ambient dimension, but that's fine. Yeah, so once you have these vectors, you immediately have 2 to the n hardness. So we just reduce problem to this. You want to find for every k, and like better for every p, you want to find k vectors which have this property in the normal p. Questions? Okay, and that's what it looks like pictorially. Say I want to find, say k is 2, and say we're talking about Euclidean norm, L2 norm. Then I give you this V1, I give you this V2, and this is my target point C. Look that every non-zero combination of them is on the same distance from the target point. But 0 is on a larger distance from target point. That's exactly the picture that we want to find for every case though. What you're saying?
This is another solution for case K.
Right. And yeah, this is another reduction for Toussaint, you're right. And we call these constructions isolating parallelepipeds because you take k vectors, like draw a parallelepiped on them, and all points except for one isolated point are on the same distance, and one point is isolated. So now, if for some normal p, for every k you can find the isolating parallelepiped with k vectors, then you are done. You prove CVP hardness for this LP norm. Is clear? Okay, our goal from now on is just to construct isolating parallelepipeds. So okay, just to recap the definition. Non-zero combination gives you distance 1, 0 gives you a larger distance. Say we're talking about L1 norm. I'm giving you right now isolating parallelepiped for every k. L1 norm is just like Manhattan distance between 2 points. So I want to say that all my k vectors here are 1, 1 vectors. They have both coordinates 1, 1. And the target point is this point with coordinates k, 1. Now, if you take a non-zero 0, 1 combination of these k vectors, which means you take the 1, 1 vector 1, 2, 3 or k times, then you end up in one of these k minus 1 point, or k points. And your distance is exactly k minus 1. L1 distance, we're talking about L1 case now. So from each of these points, the distance is exactly k minus 1. From here, though, the distance is k plus 1. So this is a valid isolating parallelepiped for the normal one. And it works for every single value of k. We just proved that CVP in the norm L1 is 2 to the n hard. Yeah.
So the vectors are 1, 1, 2, 2, and so
No. K k vectors are 1, 1.
And the target point is K1.
Sorry? Yeah, and the target point has coordinates k, comma 1. Now, if you take a non-zero combination, like non-zero, 0, 1 combination of k vectors, each of which is 1, 1, then you end up in one of these k points, 1, 1, 2, 2, 3, 3. So you basically take the 1, 1 vector either 1 or like k times. You end up in one of these points, and we're talking about L1 distance. Balls in L1 distance look like this. All of these points are on the same distance k minus 1 from the target point. But this one, the 0 point, is farther away. Okay, we just proved that CVP in the L1 norm is 2 to the n hard under the strong exponential time hypothesis. Let's talk about L2 norm. We saw a solution for 2 vectors. Do you immediately see how to generalize it to say 3 vectors? There you do.
It's not clear what these vectors are integers. So it's not clear whether you can choose them to be.
Say you're allowed to choose like whatever, like reals. Okay, right, it's impossible. Like you can actually prove that for in L2 norm, you cannot choose more than 2 vectors. You can prove a simple like inclusion-exclusion formula which says that if you have at least, if you have k vectors for k greater than 2, then the distance to the target point, like the length of the target point, will be exactly the same as all these other distances. So if they all are equal to 1, then this one must be must equal 1 as well. So it is only possible in like 1 and 2 dimensions, but not in 3 dimensions. And moreover, for every even integer p in the LP norm, basically by the same argument, you can only find p. You can only find isolation parallelepiped in pi dimensions, but not pi plus 1. Recall that for SETH hardness, you want to fix p and prove and find parallelepipeds for every single k. So in particular, this approach just doesn't work for L2 norm. It doesn't work for L4 norm. It doesn't work for LP norm where p is an even integer. It works in every other case though.
So could you tell again why does this formula behave differently for k equal to k equal to
Yeah, just basically, like roughly speaking, that's because you have absolute values for non-even integers, and because of that, you have like algebraic independence of like k distances that you are computing there. When you have even integers, but if it's like say odd integer, then it's easy to construct. If it's a sequence going arbitrarily close to an even integer, then we can construct it. If it's like for every k, we can construct it for all but like finitely, actually polynomially many in k values of p. So we can construct it in every single situation except for the most important one, L2, L4, L6 norms. And let me sketch, What sounds strange?
I mean, you would come as close as you want to know, right?
This is true, just our constructions will blow up. Like when you want to be really close to L2 norm, our construction blow up and they become exponential after that. You can approximate L2 norm by such a thing, of course, just our construction doesn't make sense, like is not useful after that. Okay, and here is just a sketch of how you can construct an isolation parallelepiped. Say you want to construct isolation parallelepiped for some p, like which is say odd integer for 3 vectors now. So you want to construct 3 vectors in some number of dimensions, for example, 8 in this case. And you want to construct some target point such that whenever you take a non-zero 0-1 combination of these 3 vectors, distance is, say, 1. If you don't take any of them, so distance from 0 to t is larger. So let's start with such a construction. It's like Hamming code, or like you write all ±1 combinations of length 3. And say the target point is has the same coordinate in every the same value in every coordinate. This is quite general construction yet. I mean, it doesn't work yet, but yeah, let's start with this. So here we can easily write down 8 conditions that we want. What are the conditions? One is that if you take all 3 of them, you get a vector like 3, 1, something, you know the coordinates, and you want to write down the distance from this to t is, say, 1. Second requirement is that some of these 2 vectors is also in distance 1 from the target point. This again, yeah.
Can you read that with the slide?
Sure.
I just don't understand. You are saying that delta of n goes to 0, so is p an integer number? I mean,
Where?
p is 0 plus...
P0 is whatever you want. It might be even integer, yeah. You can get arbitrarily close to it, but unfortunately, yeah. Other questions? Okay, so let us start with this construction and let's write down all the requirements for it. In particular, I want to say if you take all these 3 vectors, you get like a very explicit vector, like 3, 1, 1, 1, something else, and you write the distance from this vector to this one is 1. This one requirement. Then you take other like 7 subsets of these vectors and you write the corresponding requirements. So you get a system of like 8 almost equations, like 7 equations, 1 inequality basically. And okay, it doesn't have a solution. You can't find the construction in this form, but then you say, okay, let me maybe introduce a couple of more parameters so I'll have more freedom. Like I will introduce k+1 parameters and then maybe playing with them, I can find a solution to this like k requirements. Then okay, yeah. So I'll multiply the first row by some number alpha 3, these 3 ones by alpha 2, these 3 ones by alpha 1, just depending on the number of ones in the row. Except that I don't want to multiply all of this by alpha 3. I already construct this system of 2 to the k equations I have, like requirements I have. Each of them is some distance, and I just multiply this distance by alpha 3. I say distance from this to this must be not 1, but 1 over alpha 3. Distance from this to this should be not 1, but 1 over alpha 2. Instead of multiplying coordinate-wise, I'll multiply these distances. It's equivalent, except that alpha, in my case, must be non-negative. Okay, and now I have a system of these k equations, and I want to find a solution with non-negative alphas. I don't write the system explicitly, but it has an explicit form. Like each entry of this matrix of these linear equations is a huge sum of binomials, but it's explicit though. And say M is that matrix. I have k equations, k variables. I have this matrix M. Every entry in this matrix is explicit sum of binomials, just like terribly looking one. And I want to check if there exists such an alpha that for one value, for one input, I have anything greater than 1, and for all other inputs, I have exactly ones. So I just want to find such an alpha that this explicit but terrible matrix M gives me such a product. How do I find such an alpha if I believe that M is a good candidate for this isolating parallelepiped? I'm just saying, okay, note that M is stochastic. That is sum of...
Sasha, could you
Because this candidate is so, this very good like question, this candidate is so nice that if you take two guys, it doesn't matter if you take the first one and the second one, or like say the first one and the third one, the equations will be the same. It's super symmetric, so we can only be talking about the Hemingways of your assignment. Yeah?
Could you provide some intuition why you chose this parameter that depend only on the number of ones?
Because, okay, this is, you can actually say that if there exists a Lassen parallelepiped, it exists in this form for some values of target point. They don't have to be the same. When you have like 2 to the k different t's here, it's very hard to analyze. It's very hard to prove that such a thing has a solution. So we said, okay, let's say that all of them are the same. We just restricted ourselves to this case, and it happened that there is such a solution. Now you can actually know that if you set all alphas to be different things, you have 2 to the k equations, and it's hard to deal, it will be actually hard to deal with them. What we can say instead that since the things are very symmetric, then it makes sense to say that all vectors of Hemingway 2 have the same multiplicative factor. And then due to symmetry, you can be talking just about assignments which satisfy, say, exactly like some number of literals in a clause. Due to this symmetry, you are just left with k equations. So in short, this is basically, we restrict ourselves to this case because in this case M is reasonable. This system of equations is something that we can handle.
Why alpha are non-negative?
Sorry? Yeah, I said here that before I introduce alphas, I have key equations which are easy to write down. They just say some of these vectors are on distance exactly 1 from this. Now I want to say some of these vectors are on distance exactly 1 over like alpha 3, 1 over alpha 2, 1 over alpha 1. I don't want to... Sorry? I'm not multiplying these coordinates by alpha 2. This is just like a shorthand for it. Instead, what I mean here is that the distance is 1 over alpha 2. This will... Can I write it? Yeah, so what I'm saying here before I introduce alphas is that distance from vector, like say when I take all 3 of them, it's going to be 3, 1, 1, 1, minus 1, minus 1, minus 1, minus 3. Distance from here to t, 2 to the k times is exactly 1. Now, roughly speaking, I want to say that I multiply this by some alpha, this by some alpha, this by some alpha, but then the system of equations, this k or 2 to the k equations, depending on how you write it, looks horrible. What I can do instead, I can say just this distance is 1 over alpha 1. And then I basically keep the same system of equations. And the equivalent if alpha 1 is non-negative. Now alpha 1 is basically the distance. It should be non-negative. It should be positive. Okay, and so the only thing I wanna do now is the following. I wanna, for this explicit matrix M, I wanna find k coordinates alpha such that M times alpha is slightly larger than 1 in one case, and when you take like 0 vector, and is exactly 1 in the other cases. And just look at this M, like we don't know what to do with them, it looks like bad. The only thing we can notice is that sum of each row is the same. And this tells us that actually it suffices to prove that M is invertible. Then I will be able to find such an alpha that M times alpha is exactly of the form that I want. Just because I can invert the vector 1, 0, 0, 0, 0 because M is invertible. And if I add 1 to it, then I basically add 1 to all coordinates. So we'll have extra 1 in the first coordinate, and everything else will be the same. Sorry? Yeah. And so now it just suffices to prove that this matrix is invertible. And that's, again, matrix is hard to analyze, but what we can actually say from looking at it is that its determinant is just a piecewise combination of polynomials. And then, since the degree of each polynomial is small, and each non-zero polynomial has just a few roots, I can say that actually it suffices to show that one of these polynomials is non-zeros. Why? Again, what I want to show, matrix is invertible. Or what I want to show, yeah.
What means piecewise combination? Just some?
Not really. You have absolute values there. We're talking about p norms, and matrix gives you distances in p norms. And that's why you have absolute values there. And that's actually the reason why we were able to do it for non-even p's.
What is different? It's a sum of absolute values of some polynomials of degree most.
Right. And then for each value, you just have, you can open all the absolute values.
It's determined is zero if and only if
All these polynomials are zeros.
And you're trying to prove that it is impossible.
Exactly. I want to say matrix is invertible, so I want to say determinant is non-zero. For this, I can just say that since it's a piecewise combination of polynomials, it suffices to show that one of these polynomials is non-zero. And this is doable. We do prove that one of these polynomials is non-zero, and this way we avoid analyzing this matrix much. We just say clearly this is a bunch of polynomials, and here is a proof that one of them is non-zero. We're almost done with one exception, that we actually want to efficiently find alphas, in some reasonable time. Alphas are such a solution that determinant is non-zero. But since we know that one of these polynomials is non-zero and the degree of each polynomial is small, I can just go through all the polynomials, and if I know the degree is at most this, then it has at most that many roots. So if I check this many plus 1 arbitrary points, I find a non-root. I find a point where determinant is non-zero. I find a matrix which is invertible, and I use this matrix for my reduction. Yeah?
That here delta 1 equals epsilon.
Or something close to it. Yeah, I think so. Yeah, it is epsilon. Yeah.
And actually, instead of 1k, there should be also inverse of 1k, right?
No, I don't think so. It's a stochastic matrix. It is actually 1. Stochastic means sum of each row is the same. Just you normalize it by delta 2 to have exactly 1. Okay, so that's the whole thing. For every p except for p's which matter, we do the following. We first look at this construction, then say that there exist some alphas, such that this construction will be a good gadget. We need to find these alphas. We try many points, and we know that one of them will work. We find this point, get a good gadget, and plug in this gadget in that very first reduction. That's it. Now we have an efficient reduction. So to summarize, we have the following, that for even p's, unfortunately, isolating parallelepipeds don't exist, and our approach does not apply at all. But basically for any other p, they exist, which immediately implies 2 to the n hardness under SATH of CVP in that norm. Using these very reductions, you can actually prove hardness of many other problems on lattices. And you can actually prove hardness of approximation version of these problems, which is important because it's getting close to the problems on which we can build cryptography. And for them, we really want to prove like any lower bounds. So under like other assumptions, gap ETH, which basically says that in sub-exponential time, not only you cannot solve the say 3-SAT problem, you also cannot reasonably approximate k-SAT. Under this assumption, we say that even approximation version of lattice problems don't have sub-exponential time algorithms, which is getting close to what we actually want. Yeah, someone had a question. Yeah.
I have two questions. First of all, the last bullet is for everything, right?
This thing, yeah?
Previous slide? No, no.
Forward.
The last one.
One more.
Here. So the last two words are all P, so it's all the line.
Oh yeah, sure, because it's ETH. Yeah, under ETH we can prove like hardness of CVP2 as well. Yeah. For example, we saw reduction from max to SAT to CVP2, which already gives you ETH hardness of yeah.
And second question is there any dependent evidence that even in cases it is slightly easier?
Is there evidence that what?
Independent evidence that it's not just a problem with your techniques, but that in even cases even slightly easier.
I mean, it's often the case in geometry that, but I don't know, currently in terms of algorithms, it looks like it should be 2 to the n because different approaches stack at 2 to the n. And yeah, we hope that one day we'll prove it, yeah. Just not using this technique.
Different approaches for p equal to 2, or
Yeah.
do they work for
Sorry?
the known approaches? So do they work for all p, or are there any approaches?
There are, like you mean algorithms or level ones? Algorithms, yeah, there are algorithms for all values of p. They have different running times, yeah, but for p equals 2, we can do 2 to the n by different techniques. Don't know how to improve it, like even on conceptual level. Other questions? Yeah.
So what is known if you have vectors over a finite field, so the size of the field doesn't go to the right hand of the algorithm, or what is known about this type of?
So if you have a finite, like fixed finite field, then I'm not even sure we can prove. Yeah, like this bounds just. Okay, if like field large enough, then it seems that this approach might work, but yeah, I mean that's bad. It should, like field size for this approach to work, field size should be a function of k, kinda. If you want to reduce k-SAT, you need a field of size like larger than 2 to the k or something. So if you're fine with reduction from 10 SAT, then you can do it for a reasonably small field. If you want a k-SAT for every k, this approach just does not apply.
So if the size of the field is constant, then
At least I don't immediately see how.
no, I mean just something stupid. Then isn't it then true that you have just a constant number of elements in your lattice right now?
No, you still have like an dimensional space, right? Oops.
Sorry, but in finite fields, other norms. I mean, if you have a point in a finite field, and if there was a norm in a finite field, then if you apply the triangle rule to it, so you can multiply a vector so that it becomes 0. So, I mean, it seems to me that there are no norms in finite field. So, I don't know
What you mean by distance here? That's what you're saying.
maybe I'm wrong, but it seems that
Yeah, I'm not actually sure how you defined closest point here. There is a statement, like there is a version of this problem which is basically in finite field you wanna minimize Hamming distance, like you wanna minimize the number of coordinates where you differ. That's probably what Fedya means. But yeah, this is closely related to decoding error correction codes in finite fields, but that's a separate thing. Okay, then thank you for your attention, and that's the end of the course.